I think it's the best time to be a physicist now. Our technology is now starting to allow us to really revisit these fundamental questions. And one way of putting it is that if you really do generate entanglement, we could be within 5 years of really falsifying Einstein's classical theory. Achieving a large macroscopic superposition of that kind would be a phenomenal thing to do, just to show that you can. I think many people would say, wow, we didn't know you could really even interfere this. Never mind the consequences. And you know that the photon is coming from this side. That kills the superposition. Even a single bit of information of this kind. But the whole point in physics is to be sometimes as kind of conspiratorial as possible, to rule out as many versions as possible. Nature doesn't have to care about our logic. How you put a classical and a quantum system together to obey conservation principles is anybody's guess. Once you acknowledge the field, so many things come out very naturally. Simultaneously send the mass in two different directions. And double interferometer, everyone knows how to prepare the NV centers. In fact, they've even been entangled through photons. I'm writing down even the operator that you would have to measure in order to confirm that this is maximally entangled. And I think the key assumption again is this locality of interaction. You can never rule out an infinity of possibilities. Maybe energy is not conserved. Wow, that would be phenomenal. It's non-local almost in the worst possible way. It implies retrocausality, so to speak. The ripples in space-time. Gravity is just that. Maybe we should really quantize then ab initio and think about quantum space-time. Some of these early pioneers of quantum physics even wrote papers raising whether this will ever be feasible. Feynman, I think he even goes back to his wife and says, please tell me never to go again to a quantum gravity conference. These people make no sense.
Hello, welcome back to the Quantum Foundations podcast. This is the technical episode with Professor Vlatko Vedral from the University of Oxford. And if you watched the previous episode of this instalment, then that was an accessible explanation of various thought experiments to do with testing quantum gravity. And today we're going to discuss the more technical aspects of these thought experiments. So this episode is aimed at people who have some introduction to quantum mechanics already and want to have an insight into the actual details of how these thought experiments work. So hope you enjoy and thanks for joining us. So thanks Vlatko for joining us again today.
Pleasure.
And to get started, shall we just dive straight in with talking about what this the thought experiment for testing quantum gravity that you came up with collaborators Chiara Marletto and then Scott Ubers at the same time, coming up with a related thought experiment to test quantum gravity. Could you maybe tell us a bit about the background of this thought experiment, and then we can try and understand how it works?
Great, yes, it has a long history. I think it goes back to an early conference on quantum gravity, and there was a famous debate between various participants. I think Feynman was famously present there. I think he was a bit disappointed by the conference. If you read, surely you're joking, Mr. Feynman. I think he even goes back to his wife and says, please tell me never to go again to a quantum gravity conference. These people make no sense. And I think the dialogue probably he's referring to is with Herman Bondi, who's a gravity person, not a quantum person. And I think Bondi made this statement saying, how would I tell, if you tell me that something is in a superposition, how would I really be able to discriminate that from a mixture effectively? So how would I know that it's not either here or there, but I don't know where it is? So that's where this, and then Feynman had to explain this basic idea of interference. So basically Feynman had outlined already there. I think you have to look at the transcript of the conference. There's no formal paper that he was kind of notorious in that way as well, that he wrote very few papers. So basically the idea was take a massive object. I think he basically doesn't talk in detail how you would make this massive superposition, but it's clear that you have to somehow use use some internal degree of freedom, let's say the spin, and really drive the object simultaneously. It's like a beam splitter, create this massive superposition in two different locations. And then Feynman says very openly, he says, now if you think that these two couple to the underlying gravitational field, then you really have to tell me how this happens if the field is not quantum mechanical. So it goes back to this, I guess it's Schrodinger's cat. All he's doing really is, instead of using the decaying atom, he's using a massive object, and instead of having a living system like the cat in Schrodinger's thought experiment, he says, what if the field was there? And now how would the field respond to this? And of course the bottom line is that the field would not understand, if the field was classical, simply wouldn't know how to simultaneously respond to an object being in two places at the same time. And then Feynman goes further and says, well, the way we traditionally test this is of course then to try to interfere the object at the end of it and see which way it comes out. The simplest way to think about it, in fact, is to say that you bring it back to the original state. So there will be a particular kind of interferometer, the Michelson interferometer, if you like. So you create a superposition, then you undo the superposition and you say, did I return back to the same initial state? Mm-hmm. And if you didn't, if there is a chance that the object ends up in another state, that means something funny happened to the superposition. You destroyed the interference. And of course, then you can argue what this implies for gravity, and that's where it gets interesting. And Feynman never explores that. I think he just says, there is a way of testing it, put a massive object in a superposition, then what happens with gravity? And how do you know what happens? Just reunite these two, interfere the two possibilities, and see whether there is interference or not. That's where the discussion concludes. And I think normally, you would say, of course, interference is our way of proving that something was in a superposition. So if the object really interferes and the amplitudes for some outputs cancel out while the other ones amplify, just like in a two-slit, it's exactly mathematical variant, this identical mathematically to a double-slit experiment, then you could say that the interference was allowed by whatever else might have been there. So the conclusion you can draw from this is and that's all you can do, interestingly enough. You can say whatever gravity did there, whether gravity was quantum or classical, it didn't destroy the ability of the object to interfere. And now what's interesting, I think, and that's basically what I elaborated on recently with Chiara Malletto as well. We've written a sequence of papers, now there is a review on that, which maybe is the best place to read about it if you really want to know even beyond what I will say now. It doesn't really say anything about whether gravity is quantum or classical, simply because it could be that gravity is classical and that it doesn't really disturb the superposition in any significant way, so it still allows you to interfere. It's a bit like think of it like this. You have a spin in a magnetic field, and you really think of the magnetic field just as a classical magnet. There's no need to quantize this at all in any way. And now you have a slight noise in your magnet. So if this noise is really only slight, that it perturbs the spin only a little bit, you're still going to be able to observe superpositions of spin up and spin down. If, of course, if you ramp up the noise of this magnet, even though it's completely classical, all the fluctuations are classical, you can destroy the superposition. But now what does this tell you? You still have the classical magnetic field, it's capable of destroying the superposition, it's capable of preserving it as well. It doesn't tell you much. And the interesting thing is that even if this was quantum, you can run exactly the same story, and the quantum field could preserve the superposition and it could also destroy it. So it's interesting, in Feynman's experiment, the punchline ought to have been, but I think they didn't get to that point because the discussion was even how would you even test this in principle. Right. But the punchline could have been, if you don't see interference, does that prove to you that gravity is, for instance, classical or quantum? And the conclusion is it doesn't either. because both classical and quantum fields, if you like, in general, could destroy interference. And we know that. That's what we call decoherence, if you entangle to another object. So it's kind of interesting that it's not conclusive, which is not to say, incidentally, that we shouldn't do that experiment. That's, of course, a different story. And I think achieving a large macroscopic superposition of that kind would be a phenomenal thing to do, just to show that you can, because there's so many other things that could in principle fail here. It's definitely a worthwhile experiment, and there are many people who would be surprised if you take an object. I think we mentioned last time it would be something like a nanogram. It's a huge object from the atomic physics perspective. It's a very complex, so it's getting almost into the biological realm. We're talking approaching the size of a human cell. Still orders of magnitude smaller, but going closer towards biology. I think many people would say, wow, we didn't know you could really even interfere this. Never mind the consequences. But it's interesting that Feynman starts this discussion, but there is no follow-up really where anyone says, oh, wait a second, this is really inconclusive as far as gravity is concerned. And they could have done it at the time with a simple analogy with the electromagnetic field, because we know that the same argument could be applied in the electromagnetic case.
Yeah, so with Feynman's thought experiment, he kind of introduced it saying, look, there's a situation in which the quantumness of gravity can be significant, which is this superposition of the mass and whether it can be reinterfered. But when you analyze it more rigorously, it turns out that actually either result of this experiment would admit either quantum or classicality of the field. So it's not enough to conclude something about the classicality of the field, even though at first it seems like it's creating this situation where the quantumness of gravity might be significant.
Yes, and we can maybe I can say a little bit more about this, because the interesting phenomenon here, maybe for people in doing quantum physics in general, is this concept of fake decoherence, because it's very interesting. Maybe I write it. It's easier if I write. So if you put a mass in two places at the same time, let's say that mass is in position 1. I will use very crude. Maybe I could put it as a function, so I make it the same as the field. So somehow it's sitting broadly localized around x1. It doesn't have to be really a point particle. It may have some Gaussian wave packet spread, but that doesn't matter. So long as it's clearly distinct, so to speak, to a high degree from the other location. And these things usually drop off exponentially. So you make this superposition. I'm doing it very unphysically to some degree, but I'm assuming that you're going to create a superposition faster than, this is my label for the gravitational, some kind of gravitational field in the background. And usually we're thinking of coherent states that matter. You can start from the vacuum if you like. You can even assume there are no other masses in the universe. Now I introduce some mass. It's the usual story with charges as well. So I'm going to ignore the usual problems that field theory has, because they're just field theory problems in general, not specifically for this. So now you say, now it's interesting, because as I turn on the interaction, the usual argument, you will now actually get two different coherent states. It's again Schrödinger. I like to say that every physics experiment in quantum physics is it's a variant of Schrödinger's cat. It's a more complex variant sometimes, but nevertheless it's a variant. So here is a bunch of coherent states, if you like, that are localized around this mass, if you like. And then there is another bunch of coherent states. It's exactly what you would get with charge or with anything else that's quantum that you couple to. And so here is some alpha 2. I'm not even going to bother to write them down, and we can go into the Hamiltonian as well and describe all of this. So basically now you say, that's interesting, because look, if these are far enough, then you could think of these as being orthogonal to one another. So if you look at the overlap of two coherent states, it's going to go down exponentially somehow with this distance. And you could say, but it looks like the gravitational field is now measuring the mass. This is the usual argument for decoherence with it. If you stopped here And if you say, I'm going to trace out the field now, you would find if really these two are orthogonal states. That's a big question as well when you do the calculation. But then you would say, but the state of the mass is not a superposition of M1 and M2, it's really a mixed state, right? You're going to have M and X1, really all the off diagonals are gone. It's your standard decoherence, right? 1/2 if you put 1 over root 2 amplitude here. And so for X2 as well. And that's interesting. So now you say, clearly this means that you're going to destroy interference, but it doesn't, and it doesn't because of a very subtle reason that I think is being pointed out by many people. I would be surprised if the early pioneers of quantum physics also didn't have this argument somewhere. Surely they were aware. People like Heisenberg and Schrödinger knew this. But I think in the recent literature, people like Andrew and Tony Leggett are the people I would cite, who wrote very clearly about this. So now if you say, but wait a second, I made this superposition, maybe I draw it even here, I made the superposition, we are now here, the mass is entangled to whatever is in the background, but now you want to re-interfere it.
Yeah.
I hope it's visible as well.
Yeah, yes.
Now you want to re-interfere it, then basically what happens as you bring these two together is that you're dragging along the gravitational field as well. Right. So at the point where you unify the two massive states, you've also unified the two, they're not time independent, they're not position independent, if you like.
Yeah.
So suddenly when you bring these two back, your alpha state has also factored out into a single alpha that's now centered here.
Yeah.
And it decouples from the whole thing and it allows interference to take place. And by the way, this is true for lots of our interference experiments. If you're thinking of a neutron, people have done this neutron interferometry in Earth's gravitational field. If you're thinking of a neutron spin, even if you just leave the state of the spin in one single state and you just split the neutron beam, you have some diffraction in a crystal. Then the magnetic field due to the spin here perturbs all of the magnets in the vicinity, whatever they are, from the crystal, from the surrounding gas. So basically this polarizes locally the field very differently to if the neutron is here. And yet when you reunite them, all of this is gone precisely because you're bringing the two spins back into the same place, and your environment now assumes the original state before you even created the superposition. So it looks like decoherence. That's why they call it false or fake decoherence. Looks like decoherence, but actually it hasn't decohered. And it's for this reason that you can't say, the field must have been quantum or classical to collapse something, because look here, it doesn't collapse it. But it is fully quantum even, gets fully entangled halfway, but you cannot really detect this in this way. That's, I think, the subtlety there, why this doesn't work. So I think that being aware of this false decoherence is maybe the crucial point there.
So if it was the case that these actually stayed orthogonal somehow,
that's it,
and weren't didn't become the same again as you brought the systems together, then in that situation, you wouldn't be able to re-interfere.
Indeed, and I'll give you a very nice simple example of that, which is indeed, in fact, what would be problematic in any practical implementation of this, because now here we're talking about an ideal experiment where you know that it's only the gravitational field. But of course, real world, you have the electromagnetic field, which is coupling far more strongly than anything else, and that's problematic. So let's exactly illustrate what you said. You are halfway through this superposition, but somehow the mass now emits a photon, and furthermore, this is another subtlety that's very interesting, and if it's not fulfilled, then you can still interfere, interestingly enough. Furthermore, the photon is such that its wavelength, if you like, its spatial extent, crudely speaking, is smaller than the distance between these two masses, smaller than the extent of the superposition. Why am I saying that? Because I want to know whether when I get a click in my detector, I want to know whether it comes from this location or that location. If the photon is very broad, the click doesn't tell me anything. In fact, by the way, this happens in Marcus Arndt's diffraction of large molecules. He gets lucky. He's got 5 photons on average emitted during his experiment. And if you wonder why doesn't that collapse the superposition, the reason is that the vibrational frequencies, which this is a far simpler molecule than what we need for gravity, it's got only a handful of degrees of freedom, and they're all localized around vibrations that are far, far away from being able to discriminate where the thing is much bigger than the apparatus, if you like, the wavelength. So here all it takes is a single photon. You put 2 detectors and you get a click in this detector, and you know that the photon is coming from this side. That kills the superposition, not even a single bit of information of this kind. And it's simply because once you get a click, we assume that this is really an irreversible detector. For all practical purposes, you're not going to be able to undo this in order to interfere. So unlike the fake decoherence, this seems like a genuine decoherence in that sense.
Right, yeah. And if this was able to do genuine decoherence, then just this experiment alone would be able to show some difference between gravity being able to be in the superposition and cause the decoherence in this way as opposed to staying in this fixed state. Exactly,
because now you'd be getting information from the field itself directly. And in fact, I think as we talked about last time, there are all sorts of, they are more like dimensional type arguments where you are looking at the rates of emissions, for instance, of gravitons. So the same story, you could say, wait a second, why are you talking about photons? Why not emitting a graviton and getting a click in the graviton detector? But as we said last time, there are all sorts of arguments that this takes an inordinate amount of time, simply because gravity is so much weaker. So we're talking about 40 orders of magnitude slower than the spontaneous emission of light. So you're never really going to be able to, although in principle this would work, if you could execute this, it would really collapse this gravitationally speaking. In practice, you're never going to detect a graviton. So that's what stands in the way. But I think the story would be the same, you're right. And then it would tell you more about the gravitational field, clearly.
Yeah.
Yes.
Cool. And it's interesting that with this kind of explanation, it's actually gravity being quantum that would cause the decoherence to happen, despite the fact that often, I guess intuitively, decoherence is associated with some kind of
classical dephasing almost, which can happen, right? So this is the flip side of this argument where you say maybe we can even go through that because it's very interesting actually.
Yeah.
All of this is extremely interesting as just understanding quantum physics and what these things imply. You could say, oh, wait a second, and in fact these neutron interferometry experiments that I mentioned are a perfect example of this kind of stuff. So what they do is they assume that the gravity is just a classical background and it suffices to explain that experiment. But what your neutron does is it really exists at 2 different heights in the Earth's gravitational field. But the field is just literally Newtonian component. You don't care about GR at all. You don't need to describe it as a field. What you need to simply acknowledge is that at this height there is a different phase. Simply, your MGH, if you like, which is the potential energy at that height. The other one is whatever it is, and it's the difference, if you like, between these 2 heights that you are picking up in your interferometer. But now imagine that this, to write the state as we did last time, now I'm going to say at height 1, right, and at height 2. And now you say, oh, wait a second, that means there is a phase being kicked in here, but it's different to the phase that's being kicked in over here. And that's true. And if the phase was rapid, in this case, the whole point is that the phase is very stable, and you are doing your experiment on the time scale that this actually can be detected exactly. So that experiment literally was detecting, if you like, the interference of neutrons, which is due to the phase difference between the two arms, just like a double slit experiment. If you change the scattering by some phase shift, you will see this in your interference fringes. But now imagine that these are rapidly fluctuating, and they are much faster than any time scales during which you make this measurement. Then you could effectively say, oh, but my phase is so rapidly fluctuating that I'm not going to be able to detect this. I'm going to have to average this phase from 0 to 2 pi. And you know, there is this delta phi difference, if you like. And if I average the phase over the full range, I'm effectively going to get 0 here. So that's what people would call classical dephasing. So even though it results in a mixed state of these two, the story is very different. It says it's sufficient to have a classical field which is so rapidly changing, and you could do that, for instance, with the magnetic. In fact, that's what lots of experiments suffer from, and you have to correct for ultimately. But like I said, in this gravitational case, you don't have to worry about it. But it could be that the superposition is destroyed because the phase fluctuates rapidly, and it's completely classical. It doesn't require any quantum features at all. And I think that exactly is part of the problem here, why a single mass doesn't really tell you anything. If the superposition is collapsed, you don't get interference. It could be rapid classical dephasing, or it could be genuine entanglement between the field, irreversible, and you wouldn't know.
Yeah, so if we were to imagine a kind of a grid which has like classical field, quantum field, and then I guess you can have different.
That's it. That's
a thought experiment that creates each possible.
Exactly.
Matches up each outcome of things you can do with a single mass or single system, with the field actually being classical to explain it.
That's it.
Like this one leading to the mixed state, or actually being quantum to explain it.
That's it.
Yeah.
So you could do exactly interference, no interference, or even partial interference, somewhere in between, and then you can say, what can I conclude about the classicality or the quantumness of this field? And the answer is very little, unless, and I think that's a very active area of research now, unless you add extra assumptions to this. Of course, with enough extra assumptions, if you make them strong enough, you will obviously then force the field to simply become quantum, because the only way to satisfy the extra assumptions is in fact by being quantum. For instance, let me give you, I think we talked about it, we touched on that last time as well when we talked about the importance of the field description. So basically imagine that you say, I'd like my my field and the mass together to obey a specific formulation of energy conservation or momentum. Any of the conservation laws will ultimately do, and obviously relativistically they're packaged together. So then you say, oh, okay, what does that entail now? You make a massive superposition, and now you say, well, there's got to be some kind of back action. Still the argument now goes that if you want to conserve anything, the field would have to simultaneously be able to respond in both of these places. And namely, if you make this mass large enough, the phase on its own will not be a good enough account, simply because if you really want to know how does the field respond now, and you want the mass and the field together to obey, if you like, the action and reaction. It's simply Newton's third law. Then I think it's almost inescapable. I don't have a formal proof of this, but somehow it's almost inescapable to conclude that the field must be quantum, because it really ought to then simultaneously respond to both of these at the same time. And again, this is an argument that's very common in quantum in general. Think of a beam splitter, and think of a photon going through the beam splitter.
Yeah.
And now the photon records. That means for momentum conservation, the beams, never mind that it's a heavy object, for momentum conservation, it has to pick up even a tiny momentum. Whereas if the photon goes through, there is nothing to make up. So if you want to conserve momentum exactly, which means in each branch is conserved. And that's what I'm discussing here. Each branch must on its own comply with all the symmetries. And that's usually how we think about fields. Then it's inescapable to say that you must treat the beam splitter quantum mechanically. Because the classical beam splitter doesn't understand the photon taking two routes at the same, just doesn't know what to do.
Yeah.
And then we don't have a good hybrid dynamics that conserves this thing. You could argue stochastically. You could say, well, wait a second, why don't you just say half of the times? But then stochastic arguments miss the point, and this is exactly what Feynman was saying. We know that stochastic outcomes cannot mimic all the features of interference, and that's the whole point. So somehow you can try to wiggle out of this by saying, no, the beam splitter is classical, conservation is not exact, it's only on average when I repeat these experiments zillion times. But this somehow is not really satisfactory to a physicist. Most physicists would not like that, I think. And it's exactly what forces into field theory. The reason why we do everything with fields is because we like things to be conserved in this way. So somehow even the cow experiment, and you will find some papers arguing this on archive, even cow experiment, if you put this extra assumption, you could say, oh, but this proves already the quantum nature of gravity, because you're forcing these conservation laws on top of it.
And the cow experiment is this?
Sorry, the cow experiment is a single, exactly, it's the acronym, the three surnames of the Koella, Overhauser and Werner basically were I think they were the first people. In fact, there was a follow-up bunch of experiments, even by a subset of them, they refined this, did it better, did it on a spinning top to test acceleration, beautiful experiments. I highly recommend reading about this. But if you impose this strict conservation, it's almost like forcing everything to be quantum and unitary. Then it's not a surprise. Then of course you would say, yeah, of course, then we don't even need to do the experiment because you know, we are assuming all of this. So the idea to go beyond a single mass is precisely because you want to be minimalistic. A bit like, think of the kind of the frame of mind that Bell had when coming up with his inequalities. That he was thinking, I want to assume the minimum about this classical theory. I'm going to assume that I have some outcomes, I have some probabilities for these outcomes, and I'm going to assume that they're so far apart that there is no communication. And there will be infinitely many theories satisfying this. So no problem with this at all. In fact, classical physics satisfies this. And then he showed that this would get in contradiction with quantum mechanics, and of course entangled states, all of them violate this. So I think here you want to be like that. You know, Bell didn't, had Bell also introduced energy conservation, he would have said, oh, but obviously if you have an entangled state, then I'm going to be conserving things here and here, then obviously everything is quantum, no one needs to discuss anything. But the whole point in physics is to be sometimes as kind of conspiratorial as possible, to rule out as many versions as possible. So that's kind of maybe the motivation for two masses.
Because you want to simplify these, remove as many assumptions as you can.
That's it.
And if you impose this strict conservation law, you already have this strong conclusion.
That's it, because then you're saying, oh, but it has to be unitary overall. And if you say the whole thing has to be unitary, including the field, then obviously that's
You've already got your conclusion.
You've got it, you've got it.
But I guess that is one of the motivations for some people to be inclined towards the gravity as quantum direction, is the fact that if you impose something like this strict conservation law, which is quite satisfying, then it leads to the conclusion that gravity is quantum just from a theoretical standpoint.
Yes, and you're right, and I think that's people who think like this would certainly be betting on the outcome that there would be entanglement just due to gravity, because that's the only way of fully consistently describing that. Now, of course, we know in physics, and that's the whole point of physics being an experimental science, is that nature doesn't have to care about our logic, and in fact it frequently turned out that various clever people had various clever arguments, but they were invalidated. So I think here we have to, that's why I said, you know, if we didn't question nature in this way, then of course we would have already accepted a host of other things. And a person like me, even though I'm betting on entanglement as well, there is a kind of a small part of me that is thinking, wouldn't it be better if there were, that would be a shocking thing. That would really make us rethink about maybe everything, even the field theory. Maybe everything is out of the window. We need to refine all of these descriptions. So in a sense, in terms of surprise or higher information content, that outcome would be probably more surprising.
Yeah.
Yeah.
Yeah. Cool. So maybe we can
talk about
this two masses.
Two masses, yes.
Yeah.
So that's a very simple extension, and I think there is one nice subtlety as well that I should remember to mention later, which is what I will mention it as we talk now. The question will be, what do you mean by quantum?
Yeah.
What exactly are you proving regarding this field? So again, it's very similar to asking, what does Feynman's thought experiment really tell you?
Yeah.
You can always ask that about anything, and obviously there are many things left open. In fact, it doesn't tell you. It tells you very basically what ought to be quantum, the minimum that ought to be quantum. However, we have no idea. It's still, there are infinitely many theories that satisfy even this. So the idea is that you have two masses. So now you want to create one superposition which gives you this gravitational ambiguity, and what you're really testing is whether gravity somehow is generated, the gravitational field is generated by each of these masses simultaneously. But in order to do that, you need a test mass that will somehow simultaneously respond to these two fields. So very crudely speaking, what you're testing really is whether a classical behavior would be a behavior that would either recognize one location as the origin of the gravitational or the other, but it can do it in a mixture as well, but it can't do it in a superposition. So basically, I'm describing it slightly asymmetrically, even though the experiment is completely symmetric. So you have the Mach-Zehnder interferometer, which we can talk about. I'm always drawing it like photons coming in and coming out, but we are now talking about a massive object.
Yeah.
And the way you split a massive object, again, there are infinitely many ways of doing this depending on the object, and we can go into that, but I'm kind of drawing the usual Mach-Zehnder, but it's not that you would be using optical mirrors to do this.
So we can think of it more as a diagrammatic representation of the abstract way that the states.
That's it. It just literally means somehow you manage to simultaneously send the mass in two different directions, and then you have some free evolution there, and you do this with another mass. That's the interesting thing, that you need two, and this is always I should automatically say. So this is really horizontal in the sense that ideally they should all feel the same background field. Which incidentally is already an issue potentially for experiments, that working at this very at the level where the forces are very weak, you have to make sure that the local perturbations, any local anisotropies, if you like, in the background field should somehow be removed, and this is difficult. But you're thinking of this being in the same background field, and then the only field that really should matter is that what you're really asking now is whether this system behaves in a fully linear quantum mechanical way as you would expect. Namely, now you have 4 locations, and maybe we can even label them. I like to label the outer ones with zeros, if you like, and just as a qubit. They're really qubits.
Yeah.
And so you really only need to be able to handle a qubit worth of degrees of freedom. That's important. Even though they're massive, you're not really creating a massive superposition of the kind where every atom is in 2 places at the same time. You're really doing a center of mass, that the whole thing is in mass. It's really 1 qubit, quantum bit worth of this.
Yeah.
So now if you just do a very simple analysis, and I will go into the quantumness of this, if you just do a similar analysis to the cow experiment, and you say, well, the first order is that they just pick up phases, then you can see, and again, if I assume that the outer edges are too far from one another, and really we made these guys very, very close, so this distance is comparatively smaller, if you like, than all other distances. It's an approximation. You don't have to do it, but it's easier to see the outcome.
Right.
Then you have this state where initially, before again we're doing this very unrealistic thing, but I think it works in some regimes, that first you think of creating the superposition, and then you turn on the gravitational field. Of course, here they are still interacting gravitationally, but they are localized in one place. The phase is global phase, you can't detect that. And then you start to detect the phase as you spread this, and you can think of this spread as much faster than the action of gravity on this. If you really say that gravity can be ignored for all other branches than the 1-1, then you are picking up the phase in time that simply goes as, the phase is your gravitational field over r. Okay, this is the energy, and then you have h bar, and it's multiplied by time depending on how long this lasts. So r will be the distance here.
Right. So because we're in this regime where approximately this is the only significant,
let's say the only
contribution.
Yes.
Then you have this kind of approximate where this is a much bigger contribution than phases on the rest of the
exactly
states.
Right, and I'm doing that because the state that comes out is very clearly it could be a maximally entangled state. I think you can do it with other phases, and you can generate any amount of entanglement you really want to. And even in this case, of course, if you wait for a smaller amount of time, you would get different entanglement. But if you make this equal to pi, so that tells you, that's a nice formula simply because it's a relationship. If you ask yourself, wait a second, how big should this extent of superposition be? How far apart should they be? How big should the mass be, and how long should I be able to keep it? This is what you need to tell to your experimental friends, because they need to be able to achieve this in the lab. Then this gives you the formula.
Right.
And it's nice, for instance, that the mass goes quadratically as well. So if you increase the mass by 1 order of magnitude, you get the square of that. You get 2 orders of magnitude there. So some things go in your favor. And we can talk about that. But if you make this equal to pi, so this is equal to -1, you're going to get a state, and I'm going to factor things out here so that you see it immediately. You factor out state 0, this stays 0 plus 1, there's no extra phase. But with the next element, 1, you have 0 minus 1 now, because this is a maximally entangled state here, 0 minus 1. And this actually is maximally entangled. It's entangled in not in the usual way as we think of the Bell states, but it's entangled if you think of this as z basis, 0, 1, and this is the x basis, then it's entangled in this way, that z here is correlated with x and x is correlated with z. So effectively I'm writing down even the operator that you would have to measure in order to confirm that this is maximally entangled. And this would give you 2 units. This is almost like equivalent to Bell's inequalities, if you like, to test for entanglement. So it's interesting that yes, and so this is very crudely speaking how the experiment would work. And now, of course, the argument has to be made, and that's exactly the point here. The argument has to be made, why does this imply? Because look at the calculation. I never used any quantumness in the gravitational field. And I think the key assumption, again, is this locality of interaction. So what we want is that this here is done in the good old Newtonian style, where I've basically assumed that these two masses somehow magically couple at the distance. I don't give you any mechanism how they couple. I just tell you, look, there is a phase that you pick up, and it looks that's exactly what Newton would have told you had he known about quantum mechanics. So that's why that's why you need an extra assumption even here. If you are happy to accept that this is non-local, for whatever, of course we have ample evidence from GR that this is not how it is, that even gravitational waves propagate at the speed of all of this comes from a host of other experiments. But if you're happy with non-locality for whatever reason, then this is it. You are done with this, and in fact you can't conclude that this is quantum. Clearly, just a number does the job. So now
the non-locality was like Einstein's issue with
indeed gravity, this is interesting that this and that's also interesting that when he was asked at some press conference whether he himself stood on the shoulders of Newton, he said no, on the shoulders of Maxwell. And that's exactly the point, that it's Maxwell, Faraday, I guess, it was his idea, Maxwell implemented it mathematically. It was Maxwell who said, if you want to really eliminate all non-local things, even in classical waves, you really need to phrase this through fields. Charges cannot couple directly to one another. So Coulomb's law, which would be the equivalent of Newton's gravitational laws, has to be implemented locally. That's Maxwell's point. And I think Einstein understood this really well. And in fact, if you assume special relativity already, and this kind of local propagation, you are within a smidgen of general theory of relativity. You can even derive general theory of relativity from that. So this is the key input.
Yeah.
And that was for Chiara and me, that was the key question. If we now we gave a very simple version of this. It's much more complicated, but I think the simple one will suffice. But what you want is you want each of these masses to really make this local disturbance in the field. That's how Maxwell would have described it, certainly how Einstein does it.
Yeah.
And then this propagates as a wave, so it must somehow go between all of these points. But to demonstrate the point, you can actually even represent this as a single system in between. It could be a single system that couples to one of your masses and then separately couples to another mass. Now, of course, to get the right phase, you have to involve all the modes of the field exactly as we do in quantum electrodynamics. So in linear gravity, and I think we can go through that actually, you can in fact get the phase in the direct analogy with quantum electrodynamics. So the approximation you've made there is that you are in the lowest, the first order approximation that goes beyond Newton. So you're treating the field as a bunch of waves, but you're ignoring that at the higher orders, they are really nonlinear effects. Gravity itself gravitates, if you like. It causes further ripples in the field because it has energy, and anything with energy gravitates. But these are effects that are the next order of magnitude, and these kind of experiments cannot really detect them at all. So they are not significant.
Yeah, but linear gravity is enough to have this local...
Yes. That's it, to have the local description. And I can actually, maybe we could write about that if you, maybe this would be interesting to show how this works. There are lots of interesting things about it actually, that we could mention. So field theory, even when people are criticizing it and they are dissatisfied with various infinities and mathematical problems, it's a phenomenal description. Actually, it's giving us lots of things for free, as it were. Once you acknowledge the field, so many things come out very naturally. You don't have to put them on top, like conservation laws and all sorts of other things that. Even the sign of the forces between particles, that like charges repel each other in with the electromagnetic field, whereas actually in gravity they always attract each other. All of that is understood through a very simple relativistic argument in field theory. So there's a lot of beautiful things that should be said about it, which is why I think. If you're saying what's the best way of modeling this experiment as faithfully as possible, I would say the best choice is really linear gravity. We just don't have it. It just ticks so many boxes that it would be illogical, even though of course they are not ruled out experimentally, but it would be illogical to do anything else at this level. So it's a very simple model. You are thinking of the two masses as you can even, this is going to be some kind of hybrid. A hybrid description where you are thinking of the masses as effectively being non-relativistic in some sense. They are very slow. They are just they don't move fast. So even though I'm claiming that this is what linear gravity would do, it's not the full field theory because you don't need it. You really don't need to take any extra effects into account from this. So you are somehow assuming that there is energy of each of these, and you can even say mc squared if you really think about the stationary limit. So basically, when you're making this superposition, it's so slow, it's adiabatic, if you like, that this is the only, you don't need to take the kinetic energy into, you can, it's obvious that that's easy.
Yeah,
so then you have
this regime we don't need to.
You don't really care about it, and in fact you can always add it to the mass effectively, whatever corrections there are. So then you have the two masses, and these are just number operators saying this is the energy of mass 1, and we are assuming that they're identical because that's the easiest thing to produce experimentally. And then now is this key a key feature that you want each of these masses to somehow independently. So there will be some degrees of freedom that are due to gravity, and I'm going to write it just as a single. As a single mode at the moment, and this is the frequency, let's say the relevant frequency of the gravitational field. Normally, of course, you would add up, there would be infinitely many modes, but I just want to show how this already intuitively you can see how the forces come out. This is the same argument as in QED, and then you have, so this is the free Hamiltonian, and of course this would just give you these global phases that would go as e to the I mc squared times time, and I omega t, and now you say, okay, there is a coupling which can go with whatever number. There is a coupling between gravity and the field, and the usual way you describe this is that you would talk. So in electrodynamics, I'm not sure where, maybe just to write it here. In electrodynamics, in this regime, when you can ignore the currents, you can ignore the motion of the charge, you would have the charge density times the zeroth component of the vector potential. So basically, your charge simply couples to the field, to the relevant underlying field. Your charge now is your mass, if you like. So here it would be B1 dagger B1, which is saying if the mass is there, whenever you have one there, it's going to act. And then you have, for two masses, you can see that this generalizes to anything there. And now it's coupling to the field. And the field, in all our field theories, whenever you're describing, whatever you're describing, looks like something like A plus A dagger. It's going to be a component of the creation and annihilation operators. Of course, electromagnetic field, you're creating and annihilating photons. Here you would be doing gravitons, but you don't need to assume that in this model. Effectively, you need a term of this kind. And now the key thing is that this only couples to that at the point where the particle has a non-zero probability to be. So this thing, if this acts on the vacuum state, which means the particle is not here, it would simply be irrelevant what the action, it wouldn't perturb the field at all. It only perturbs the field at the point where this guy is, and this only perturbs the field where this mass is, and that's usually how field theory works. And then of course you exponentiate the Hamiltonian and you run it in time to see what happens later. How do they now evolve together and get this attractive force between them? So that's kind of the basic thing.
Yeah.
And immediately here we can make this comment that if you look at this kind of linear regime, which is the same as QED for gravity, you have the usual story. If you say what is it that doesn't commute with what, it's always the energy, so to speak, the energy operator of the field, the total energy of the free field, and the field operator, one of the components. So here again, note that you only really need one of the components of the GR. In a way, again, crudely speaking, there are some technicalities, but you don't need to involve the whole of Einstein's with the 10-component tensor. Only one of them. So it's effectively like a scalar field. It's very simple to treat that. And if you choose that right component, you will then be able to derive if you like, the attractive force between them.
Right.
And I can even write that down, maybe if that's useful, how the calculation would proceed. But it's exactly, there are many ways. I don't know how many ways there are. So these kind of linear models have exact solutions. In fact, and we are very lucky when we get a linear perturbation, because we know how to diagonalize the Hamiltonian. But you could, for instance, simply compute. You could start with the two masses in some locations. So maybe again I use the notation that was very similar to before. You could say there is a mass at x1 and a mass at x2. And then I could assume on top of it that the field is in the vacuum state. In fact, it's immaterial what the background is, because what you care about is the displacement when you put the mass in. So whether you start with alpha and go into alpha plus delta alpha is completely irrelevant what alpha is, because you only care about the offset, really. And now you exponentiate, let's call this the Hamiltonian. You just run the usual calculation. And to cut the long story short, and I could show it to you in a different. So you would now look at exactly the overlap between the same state. It's kind of what a field theorist would call vacuum to vacuum, right? And you would see that this, in fact, again, you have to be careful with certain infinities that you have to ignore, like the self-energy and so on. So we're ignoring lots of factors. We're ignoring certain other things that I'm happy to go in. But like I said, these are the usual things that you have to deal with in any field theory, and we consider them kind of resolved, at least to some satisfactory degree. So this would give you exactly this phase that we said. After kind of getting rid of certain infinities and so on, it will give you the phase between. In fact, here R is simply your x1, if I call them like two positions like that. So this is like a standard field theoretic calculation. And the main thing, again, for causality is that if you ask, if I made a perturbation at point x1, how long would it take to get to x2? You will get exactly the speed of light. It would be fully causal, local in that sense. Everything would be conserved in a local way, just like with Maxwell. Just like with point, there would be like a Poynting's theorem equivalent in linear quantum gravity, and it would be satisfied. So the field together with the masses would satisfy all the symmetries. And so that's interesting now that you are simply identifying the same features, if you like, of the gravitational field as non-commuting. This, by the way, would be, if you want to link it to Einstein's treatment, this would be, like I said, in the electromagnetic case, it would be the vector potential that couples to your current. And that's basically a relativistically invariant way of doing. It's a 4-vector, current meaning the density, the static density, and current in x, y, and z would couple to the vector potential 0 that couples to density and x, y, and z. And if you multiply the two 4 vectors, you get an invariant quantity in relativity. That's why the relativity forces you. Here, your metric is your vector potential, if you like. So this would be, as it were, the G00 component of the time component of the Einstein metric tensor. However, I should say that in this low regime, we tend to think about the perturbation of these guys being quantum. So you are writing G00 as being effectively Minkowski, without gravity, and then you have this perturbation that people usually call H00, and this H00 gives you Newtonian forces, and it's in fact this guy that you would be quantizing. That's this here, and this energy is simply the conjugate of that, which is something like the time derivative of H. So this and this if this is the right picture for gravity, this would be the non-commuting. So you would be proving within this theory that that's what doesn't commute there.
Right. Yeah, and that's the signature of quantumness, of gravity is non-commuting.
That's it.
Operators being in the Hamiltonian.
That's it. So it's phrased very conservatively. The way Chiara and I really did it is to even go beyond this and say that the least you can say, even if you deny this as being the right model, but you accept locality, that somehow it has to propagate to nearest neighbor, then next to nearest neighbor, and so on, like the usual, like a chain of coupled harmonic oscillators, if you like. That's the usual model. If you assume that, then entanglement detection in this experiment would at least force you to say that some degrees of freedom must not be non-commuting.
Right. So even if they're not.
Even if they're not exactly,
there's something which.
That's it. Because otherwise, of course, this description couldn't do that work for you. It just couldn't simultaneously couple all of these charges. But yes, so that's where someone has to be really careful that I'm making an extra conclusion here. I'm saying let's take linear gravity. It's the most sensible thing to do. What else? That's the only description we have, and then that forces you to do this. And it's interesting that you see. I said that this would then be interpreted as creating and annihilating gravitons, and even though we mentioned that you can't detect them, it would take much longer than the age of the universe to get a click in the graviton detector. What's interesting is that even though, if you accept the linear model, then these creation annihilation operators really represent graviton creation and annihilation. So if you do assume that this is the right Hamiltonian, then you are indirectly proving the existence without, even though a detector can never really detect a graviton, it would take an infinite amount of time. Basically, here you are indirectly saying there've got to be these degrees of freedom that don't commute with the energy, for otherwise we really don't know how to account within this model. Which is why, again, some of these things would be interesting, because a failure of that experiment could signal all sorts of things. It could even signal that maybe this is not the right way of describing gravity. So there could be many conclusions there.
Yeah, that's interesting that you can reinterpret it as a graviton detector in the indirect way,
and I think many
signatures of a graviton.
That's
somehow.
right.
Yeah.
That's right. Many people have done that, and in fact, again, it goes back to this thing that we touched on, that if you make sufficiently strong assumptions, and here it doesn't get stronger than this, I'm even giving you the Hamiltonian of how this ought to go, then obviously you're putting the answer right there. You're already telling me gravitons are sitting in the Hamiltonian. No surprise that that's what the experiment then proves. So that's why I think we wanted to be as kind of minimalistic as possible, right? We wanted to strip it down to the simplest components and say, no, what it really tells you is that there are no, and this is an example of how non-commutativity would come in, but it could be some other. For instance, there are these alternative approaches which argue that you should quantize space-time directly. So it's not that the field components don't commute. They may not commute. That may be a consequence. However, at the most fundamental level, it's the space component that don't commute with one another and with time. So some people are saying, given that Einstein's the spirit of GR, at least the way he thought about it, not everyone has thought about it like this, but he thought about it, it really is just the ripples in space-time. Gravity is just that. It's the curvature of this four-dimensional space. Maybe we should really quantize then ab initio and think about quantum space-time. It's not clear what this means, but there are approaches like loop quantum gravity where they're really thinking, what that means is that what doesn't commute now are the operators for length, for area, for volume. So for instance, the operator for volume wouldn't commute with the operator for area, and indeed you can think of this as areas and volumes in that sense. So instead of having graviton creation annihilation, I could write an even more possibly fundamental Hamiltonian that gives rise at some higher level to this. Then you would be maybe reinterpreting this differently. You would say possibly the field doesn't commute with the energy, but that's a consequence of the fact that space and time don't commute. But obviously, now this requires even further assumptions. So for me to say, this kind of double two masses interferometer confirms that space-time is quantized, it's a big jump, because you really have to then commit yourself to even more than that. So
right. Yeah. So in terms of what the outcomes of the experiment would tell us, if you do the experiment and you do verify that they're maximally entangled by doing a Bell type test, you verify that, then that tells you that there must be some non-commuting operators in the field, or space-time, or somewhere. And if you find that they're not maximally entangled, or they're not entangled, what can you deduce from
right,
that?
so that's also an interesting, a bit like you're asking the same question as in Feynman's experiment. What does it mean? What does the flip side of this imply? It's certain, and of course we're assuming that you are confident, because you can never with a simple single experiment rule out other explanations. And in fact, people have been very quick to point various things out. How do you know that this is not communicated by another field, by a fifth force? Who knows? This is true in all of our experiments. You can never rule out an infinity of possibilities, but you have to kind of view them in the light of other things that we understand in science, and they have to comply together to give you as coherent a picture as possible. So if you really eliminated all of this, if you think, it's unlikely that there is something like another force or anything like that, doesn't really make sense as an explanation, then probably you would have to start to think that maybe gravity is not really quantum. So one possibility is certainly that you go into what I was describing earlier as some kind of semi-classical descriptions. You could say, but maybe, and there are many people advocating this. Again, like I said, the price to pay is that you really have to revisit symmetries. How you put a classical and a quantum system together to obey conservation principles, to obey the equivalence principle in general relativity is anybody's guess. Actually, then this is a big. That's why I said a negative outcome would almost be more interesting, because we'll be rethinking the foundations of the whole subject. Maybe energy is not conserved. Wow, that would be phenomenal. And in fact, as you know, early pioneers, people like Heisenberg, did suggest when there were missing particles that they couldn't account for, they were saying, energy is not conserved. It's quantum. It's weird. We've already bought, most of these kind of weird stuff. Now maybe even energy is not conserved. But so far we never had to go down that road. There was always something else that explained to us this. So that could be one thing. Another interesting possibility, and I think this is worth investigating, is that maybe it doesn't act in a local way. Maybe it's not a field. Maybe you really made this. The key assumption was that there is no direct interaction between masses. However, that's exactly what gravity is. And in fact, there is a whole formulation that originally is in classical fields, in electromagnetic fields, due to various people. We are talking pre-quantum, certainly. The most famous would be Feynman and Wheeler, which was an attempt to eliminate fields precisely because fields give us some mathematical inconsistencies and uncomfortable infinities that we have to deal with, or we have to throw them away, or whatever we do with that. So basically they said, wouldn't it be nice if there was just charges? But then the theory becomes hugely non-local, because what they really need is even an instantaneous interaction is not enough. What they need is a future boundary condition. They need a future absorber, a future charge, if you like, which is going to somehow mediate by receiving signals from the past and then sending them back from the future. So it's non-local almost in the worst possible way. It implies retrocausality, so to speak. But then when you add all of these effects up, miraculously, you recover the usual description. So the level of charges, and I think their argument was you never measure the field directly. It's always through charges. So let's see if we can even get rid of the field, but maintain that nothing nothing can be measured to travel faster, even though the description contains these things. Could be the gravity is like that. Hoyle and Nanlicker have a whole book. After Feynman and Wheeler, they said, oh, this was done for electrodynamics, let's do it for gravity. And actually, it works, apparently, according to them. There's a whole book giving you an account of the gravitational action without the gravitational field. To me, this would be a phenomenal thing as well. And I think the reason why, the question, of course, is how would you even begin to test this? So this would immediately lead to questions like that. But if you really start to go in that direction, then it seems to me we ought to revisit other fields, because maybe now what we discovered with gravity could indeed then be true for other fields, and maybe these accounts should be taken more seriously. Again, I think the probability for that is very low. It's a bit like with Bell's inequalities, that when you get a negative outcome, you have to, or a positive outcome even, you have to then revisit the assumptions and think which of these fails if I get this outcome. And I think here a number of things could fail. And then of course you look at other experiments and other directions where you're then, you're basically placing your bets on what you think is more likely than others. And no one knows. I think it would be exciting.
Yeah, cool. So maybe now can you tell us a bit about the experimental proposals that you've been thinking about, and how we might actually work towards a test?
Yeah, there are many exciting ones. The nice thing again is that, and maybe this is what Chiara also likes to emphasize, is that I will say this before I go into a concrete one, that again with gravity, anything that has energy gravitates. So if you don't have to spatially split, because you could be thinking, well, making a spatial superposition could be challenging for a large object, and it is challenging in fact. But you could say, what if the object is in the same place, but I make a superposition of two energy states? Which, by the way, we get all the time. That's what quantum mechanics is all about. When you excite an atom, when you prepare an electron inside an atom in two different levels, in a superposition, you've effectively created a superposition of two different energies, and therefore it's just that this is tiny. Even this has an effect on the gravitational. Even this perturbs local gravitational field in two different ways. So if you could have, so it's not enough, obviously, and I think that's why this sounds less realistic than the spatial superposition, because the difference between energies would have to be really huge, and whether you can do this in one location is a question. So I think after a long search for the right system, and I think Sugato has suggested these nanodiamonds. The reason being again that nanodiamonds are crystals like diamonds in general, and they are very easy. They are already used in quantum information in all sorts of ways. Usually metrology, which is exactly what we have a particular instance of trying to measure a very weak disturbance, because gravity is weak. And so metrology is all about that. Can we quantumly detect things that are not possible to detect even by classical means? And you could see why many people would be interested in these kind of things. So basically here you are importing a technology that's already widely used in many places, which means we know how to do many things with this, and that's maybe what I want to describe. But what no one has done yet, and that's also exciting bit, is even Feynman style experiment has not been done. That's why I say it would be phenomenal to even achieve this in the first instance. So Sugato had a variant with these NV centers. I will explain what they are. He had a variant where you do a free fall experiment, and in fact a free fall could eliminate. I was saying that it's very important to have the background field which is uniform, that you don't have an extra phase kicked into either of these or any of the four locations, because of course that would contribute either to different interference or to destroying interference. So Sugato was almost imagining free fall. You could even think on a satellite. If you could mount this technology on a satellite, it would be a great place, as far away from anything else. But it seems to us that even in the lab you could do it. And of course in the lab you have a much better control than mounting this on a satellite. That really would be a level of another order of magnitude harder. So what the idea did, so these are like diamonds that have usually a deliberately, although you don't have to do it deliberately, naturally occurring diamonds of course are impure. So that means that in a lattice of carbon atoms you will have a vacancy, you will have a bits, sometimes a place where an atom is missing, if you like, and you would have other impurities where other atoms are present. So this is why this is called nitrogen. There's a nitrogen, and vacancy means an empty slot.
Right.
And if you do, it's relatively intricate. I think you wouldn't quite do this as an undergraduate in physics. You could, maybe if you did chemistry. You could actually analytically more or less get the energy level for this. And you could show that it behaves for all intents and purposes as a single spin. I'm cutting a long story short. It's not quite as simple as that, but you have a handle there on the spin degree of freedom, and you can certainly you can flip the spin and prepare any superposition of spin states. So exactly like Stern-Gerlach. That's why I think effectively what you're doing is Stern-Gerlach but with a much more massive object. So that's another thing. There is no limit to how massive this could be. When you engineer this, you get a lattice, you get an array of these NV centers. You can shine a laser and knock them out, and you could almost make any mass you like. And what limits the mass is many other requirements from the experiment rather than the engineering of these NV centers. So you have this single spin, and what you want to be able to do is use this spin in order, that's the handle that you have on the system to make a superposition, just like in the Stern-Gerlach. So you have this NV center, and somewhere inside you know exactly where this is. So this would be done in advance, this kind of studying of the center, doing all the spectroscopy, and it's nice also that you can optically make these magnetic transitions, which means you have a fast preparation, readout. All of these are amazing things that have already been used in all sorts of, even in violation of Bell's inequalities between NV centers. So there are all sorts of things that are already close in some sense. So you have this spin up and spin down, and if you make it in a superposition of the two, as we know, and you make a magnetic field gradient, because the energies of course go as plus minus the magnetic moment times the B field. If it spin up, it would drag this system in one direction towards one minimum, if you like, in your magnetic field, or towards another, and these two would then be split coherently. That's kind of the idea, how to make the beam splitter in the case of. So there would be an awful lot of preparation. Then you would have to by using a laser field, knock them out of this array. And in fact, you could knock out two simultaneously, because for this experiment, you would really need to be able to do two of these at the same time. But like I said, even one is interesting, how to do this. Then you would engineer very carefully in this trap your magnetic field, which is another challenge experimentally, because the question is really of the resolution. How small can this distance be to achieve the gradient large enough to split this thing? And remember, this mu goes inversely with the mass. So that's where, you'd like the mass to be as large as possible, and it's fantastic that NV centers can be very heavy for gravity. However, when you're splitting them, if you make this too large, then you're going to make this super slow. You're going to have to maintain coherence for so long that all sorts of other things would now destroy you.
Right.
So that's actually what our collaborators in Turin, Marco Genovese and his group, are exactly investigating now. They're doing various, and we're doing together actually various feasibility studies. Is there a region, I was going to say a sweet spot, but having one spot would not be sufficient. You want to make sure that there is a region around that sweet spot where you have the right parameters to do this. The good news here is that when they're localized in one place, people have showed that the coherence times of these spins is is extremely long compared to, again, anything we're talking seconds. People are talking tens, hundreds of seconds, which is a good news, because I think that almost comes out as the right number, how long we would need to keep this in a superposition. And it's coupled now to another, so this is half of the experiment, if you like. The other half now is to engineer them exactly in the opposite way, these fields. And again, remember, any fluctuations, classical fluctuations in the magnetic field should be as minimum as possible. That's kind of where the noise comes in. Any fluctuating neighboring spins should also be eliminated. And actually there are all sorts of active ways in which people do this. So the reason why you can do this for 10 seconds is because there's an awful lot of error correction there. So they're beautiful dynamical decoupling, spin echo kind of style, and I don't want to go into all of these details, but they're all very interesting there. And then you have to recombine them, like in any interferometer, and then ask, measure the final state somehow. So, in this Mach Zehnder type, it would come out one way or the other. In this case, I think you would be measuring possibly the spin, whether it's spin up or spin down, or spin left and spin right would be the kind of correlation. So we have a technology which has it's ticked a lot of boxes, but individually, no one has really put it together in the Feynman-like manner. This is what I think Feynman would have loved to have seen, something like that.
Yeah, and so this would be the Feynman experiment.
This would be exactly the Feynman. And I think my feeling is that whoever does that already, that's a phenomenal experiment. That's nature from cover, if you like that kind of language. So that's a huge challenge. And now the challenge, I should say, why? So I already said, having a mass large enough for gravity is great. However, too large is going to make this too slow for the coherence to be maintained. But there is an extra complication. In fact, there are many, but I'm speaking as a theoretician now. What I see as the biggest. The problem really is that, again, you could say, oh, well, why don't you make it less massive, but make these two arms that I drew very close to one another. So this is your second interferometer now, and let's say they're so close that the main phase built up is here. Now you enter into these van der Waals forces. So basically, what happens, even though they start as neutral objects, and you know that they're neutral, electrostatically speaking, what happens when they are close to one another is that, as we know in quantum mechanics, neutral objects become polarized because the positive and the negative charge is never really equally distributed anywhere. It's only equally distributed if you're far enough that you're kind of coarse-graining this. But in fact, in a real, even in a neutral atom, of course you have the electron at the outer end, quite far, if you like, from the nucleus. The distance is big, but for another atom to see that distance, they need to be relatively close to one another. And then as they get close, the negative charges, the electrons, are now closer to one another than the positive. You're going to see an excessive field due to this, and that's your dipole coupling between neutral objects. In fact, lots of chemistry is all about this, these kind of forces. And if you ask yourself, so where does this happen roughly? It happens around the 100 micron distances. So if there is this of course depends on the details of the system, but I think this is like a conservative estimate that most things really below this would start to have some extra electromagnetic effect. Now, one thing is to say, well, let's go beyond this. And this is why you are then saying, that means I probably better up my mass. If I want to remember, the formula was like that. Yeah. If I want this to be equal to pi or to 1, close to 1, then if I make the distance bigger, which means the phase is smaller, then I have to either up the time, but maybe I'm reluctant because there is intrinsic decoherence that kills the spin, or I have to up the mass. But then I'm sitting with this idea that if I up the mass, it's slower now. Then I have a problem with time. They're not independent. Right. And that's why I'm saying there is a kind of, it's a multivariable optimization. But the nice thing is that is that the Torino group showed that there is actually a region where you could think about doing this, and it's feasible.
Right.
So the other thing I maybe should mention is that you could approach this in a more pragmatic way. You could, for instance, if you understand your systems really well, you could take into account the van der Waals interaction. So you could now say, oh, there is this phase, there is e to the I phase gravitational, but there is also electromagnetic phase, but I know exactly what this number is.
Right, yeah.
So then it tells you that if you reach maximum entanglement and you know that this on its own cannot do it, then it must be an extra phase. Even this is possible. Again, the only danger is that we know that this is usually much stronger than that. So you don't have that much room to maneuver, because if this really is orders of magnitude bigger, then you're never going to see this in the fluctuations. So that's kind of the complexity. So double interferometer, like I said, everyone knows how to prepare the NV centers. In fact, they've even been entangled through photons. So one of the Bell tests by Hansen group in Holland was exactly to entangle two NV centers at a large distance, 1.3 kilometers.
Oh.
So they separated one. Then they did center photon now. Not a graviton, which would be kind of the other explanation. Send a photon that gets absorbed here or here, and that gets them to prepare up, down, plus down, up state of the spins. And they want them far apart because they want to make sure that when they measure one of them, so they did Bell's inequalities, and they actually closed the locality loop call as it's known. Here you wouldn't care about that. Here you're testing something else. But somehow that was interesting that we do have the technology. We know how to entangle them. We know how to keep them entangled for a long period of time. However, the Stern-Gerlach has never been done, and that really is a challenge.
Yeah, interesting. So there's a kind of pathway to a way of doing this experiment with a kind of feasible region of parameters.
Yes.
And what do you think is, say, the bottleneck of doing this one, of kind of thinking about where we are in present day? Where are the experimentalists trying to push the boundaries right now in trying to implement this?
Yes, I think the bottleneck really is even in the, so of course there are many issues as we touched on when you have two, but already a single one is difficult. I think that's the difficulty, and the difficulty is even this goes back even to the early discussions of Stern-Gerlach experiment, Niels Bohr, and all of these other usual suspects. I think they basically what they were frequently wondering is whether we would even, because remember, Stern-Gerlach experiment finishes here. In a sense, you split the beam and then you have a detection of your atoms, and then they make an imprint, one part of the screen or the other one, and that's what you're observing. It's a bit like a double slit experiment. However, what you need to do here, that's not enough really. That's only confirms correlations in one basis, if you like. What you need to do is to be able to re-interfere them. So I think arranging the fields in the right way and then inverting them in this way is a huge challenge. That actually has never been done. And I think some of these early pioneers of quantum physics even wrote papers raising whether this will ever be feasible. This touches on this question of irreversibility. That even though quantum mechanics is in principle reversible, maybe there are certain things you will never be able to reverse. And that would be a shame here, is if what's preventing you is simply recohering. And of course they can fail for all sorts of the magnetic field, the coherence time internally of these guys, all sorts of things could actually be problematic. So I think that is hugely interesting. And then what I would do with this, even if you show interference, what would be now interesting, and again this is why I'm hopeful about this, because an interferometer of this kind could even be very practically applied. For instance, if you take another mass but not in a superposition, just to measure a weak gravitational field from a nearby object, This could be just a classically local, even 1 kilogram. Put a 1 kilogram mass next to this. Now we're talking a cow style experiment that we described before, but not Earth's magnetic field. What you are looking at is the difference that this mass imprints as far as gravity is concerned on these two paths. Can you how small is this guy? This could even be the world record in detecting the most sensitive gravitational. No one has done that at that level. I don't remember now what the masses are, which were the smallest, but they're quite large. Actually, gravity is one of the worst confirmed things, so to speak, in terms of the decimal places. Simply because it's the weakest force. So to me, this already is amazing. You know, can I detect a nearby object, even classically speaking? Can I detect it through quantum interference?
So it'd be like a super sensor for gravitational fields.
That's
around.
it. Gravitational fields. Of course, if you know that other things are affected, this could even detect these other things. But gravity being the weakest, of course, would be what you would want to apply it to. And already this would be even closer to what Feynman had in mind. You know, does this mass make this collapse? Even a static mass, would it really collapse this superposition? That's interesting.
So it would be, kind of exploring those different scenarios of what can happen in Feynman's experiment.
Yes. And then there are variants. I think that Mark Kasevich at Stanford, I think frequently motivates his experiments. He did a similar experiment with the Bose condensate, which is kind of, even at the massive end of Bose condensates, you're nowhere near the masses that you need here. Like I said, here you need a nanogram, which is a huge number of atomic units. These Bose condensates may have up to billion atoms at the large end of the spectrum, and I think we're still 10 orders of magnitude below what you need for this mass. But he did a nice set of experiments, in fact, where you're throwing a Bose condensate in a kind of free fall, but along different trajectories. So that would be your spatial superposition. And then he had arranged a kind of massive object of this kind. I think it looked a bit different, like a ring. But basically he arranged that one of these paths is much closer than another one, and he looked at whether he could detect these things. And he sold it as a gravitational Aharonov bomb effect. So it's in a way you can show that you could be in a regime where the field is field, meaning there is no acceleration difference between these two paths. They really suffer the same acceleration, g. However, you are still getting a phase, and the only way you can explain the phase is through the field itself, not through the gravitational field, but through the vector potential, if you like, through the g mu nu, as we discussed, rather than through the field. So there is a host of other interesting bits of physics, I think, that you could test. Which, even though you would call it classical, maybe you wouldn't be confirming quantum gravity. I think they're still outstanding issues.
Cool. So we've kind of, to summarize our discussion, we've kind of come full circle in a way from, we started talking about this single mass experiment that Feynman was suggesting for testing aspects of quantum gravity, saw that it actually doesn't really distinguish between quantum and classical gravity, because you can explain all the different explanations using either one in different regimes, and kind of different explanations you can come up with. And then we talked about the two mass version, where you can put them in superposition, do a Bell type experiment, and check if they've become entangled. And that one actually, if you find that there is entanglement, it does tell you something very general about the field, that it has these non-commuting aspects. And then we discussed how a model, this linear gravity model, is kind of a local gravity model for getting those non-commuting parts and analysing these kind of thought experiments, but the conclusions are actually very general, in a similar way to Bell inequality experiments. You have these general principles, you've kind of removed the conservation law assumptions or specific type constraints. And then when thinking about actual ways to implement them, you showed us how to, this proposal for doing it with the NB centres, which is a kind of, has these potentially realistic regimes for implementing
Yes.
the experiment. But even before we get to the two mass case, it would actually be really cool just to do the single mass
Indeed.
case, and so
Yes.
that is actually something to kind of aim for as a next step, is to implement the single mass superposition experiment, which of re-interfering it, and that would actually have these interesting implications for sensing and kind of applied breaking records of the
Yes.
applied technologies that we have.
Yes, it would certainly be extremely sensitive. The issues, of course, when you go into the applied direction are sometimes even bigger and requirements more stringent. So someone would say, okay, you are doing it in a static setting on an optical table. What if I want a portable detector? Then, of course, you have extra engineering complexity. Could you actually even move this around and do these things? Could you mount it on a satellite, as we said? These are all even more complex problems, I think, but certainly it would give you a proof of principle for probably the most sensitive measurements you could make.
Yeah, cool. Yeah, that's all really interesting. Thank you for explaining everything. I think that was a nice summary through the different ideas, and I'll put links to the review paper and maybe one about the NB Centre proposal as well in the video description for anyone that wants to take a deeper dive. So yeah, as we wrap up, is there any final comments you'd want to make for our audience?
No, I usually like to say this, that I think it's a great time for physics now, because you listen to various people and they complain how we haven't had a new theory for 100 years or so, and it's getting kind of less creative or more boring or whatever people say, and I'm actually I feel very differently. I don't identify with these views at all. I think it's the best time to be a physicist now. I think our technology is now starting to allow us to really revisit these fundamental questions. And one way of putting it is that if you really do generate entanglement, we could be within 5 years of really falsifying Einstein's classical theory, classical GR, which is Einstein's theory of gravity. That to me sounds phenomenal. Already doing that, falsifying that, seems to me a huge milestone. Even if we don't quite understand how we ought to proceed within that, I would call that a new revolution in physics of sorts. It would tell us something non-trivial, I think.
Yeah, cool. So hopefully our audience is inspired that physics is
I hope so too. Come and join us.
Yeah, and thank you for joining us today for this episode, and please look out for more future episodes about aspects of quantum foundations. Bye.
Bye.
Cool.
Perfect. It was nice.